Welcome everyone to our OSMOSE webinar today on 3rd of May on the optimal mix of flexibility in long-term scenarios. And we had a lot of registrations, so we hope that maybe a few more people are dropping in, but we want to get started on time. And I would like to start with a short introduction of the OSMOSE project, and then the webinar is set into 3 parts with a Q&A at the end. And feel free to post your questions in the chat already during these 3 parts. So first of all, what is the OSMOSE project? It's an Horizon 2020 project between 33 partners from 9 countries in Europe, led by RTE. And it ran for the last 4 years and 4 months. And the objectives of the project were to get a general understanding and improve this understanding of the future needs and sources of flexibility in the European power and energy system. And one part of the project was here to look at modeling tools for the quantification of flexibilities, especially in long-term scenarios, looking up to the 2050 time horizon. At the same time, we also wanted to look at the implementation of some innovative flexibility solutions, and this has been done in 4 large-scale demonstrators that were led by TSOs. And to look at the general structure of the project, we have on the left-hand side the mentioned simulations of the long-term scenarios. So here we identified future needs and sources of flexibility. We developed new tools and methods for the assessment. And this was split into 2 work packages. The first one of which, work package 1, the webinar is on today, and the second one, work package 2, looking at market designs and regulations. This will be tomorrow. So if you're interested in that one, please feel free to sign up for it as well. And then we have the 4 demonstrators looking at grid forming solutions, at different multi-service solutions, and near real-time cross-border energy markets. And the webinars on these demonstrators already ran earlier, but on the OSMOSE website, you can find a lot more information on those, including some videos showing the details on the demonstrators. So now looking at this first work package that we called boldly optimal mix of flexibilities, we had the objectives to, first of all, identify a cost optimal mix of flexibilities for the European power system. And here we wanted to especially focus on energy mixes with a very high share of variable renewable energy sources. And we looked at scenarios for 2030 and 2050 in a holistic vision of flexibility. So we wanted to look at any available lever we could think of. So that means, first of all, we needed a workable definition of flexibility, not just as a buzzword, but with some concrete content behind it. And we were setting up a methodology in order to come up with these scenarios and the analyses, looking at relevant temporal and geographical scales. So going enough into detail here with transparent, replicable, and tractable real data. And we wanted to do this as far as possible using open source tools with some additional own developments. So looking at the first part now, the modeling to capture flexibility, what has been done here, we basically looked at so-called capacity expansion models. So for those of you who are not familiar with them, just a quick introduction. Basically, the capacity expansion models looks far into the future. So in terms of our scenarios in the years 2030 and 2050, and they're minimizing the total costs of an investment pathway. And we use a couple of inputs for that. So we have the case study structure, so the technologies that we want to include into our scenarios, and also the investment period. We have a lot of parameter values like costs, technology potentials, and so on. And because this obviously is a very complex problem, what these capacity expansion models usually do is that they use only specific time slices. So they don't break this down to every single hour of all the years that we are considering, but we're just looking at a couple of time slices that are taken out that should be as representative as possible. Yet there are a couple of shortcomings if you use these reduced time series in such planning models. And obviously, you can see here in this picture that if we go down to very low temporal resolutions with a high share of variable renewables at the same time, then there will be a significant share of lost load in the power sector when we actually do the hour-by-hour modeling to check if the results are working. And we've tested different methodologies, and they all have their own shortcomings. Which is why we thought of some other methods of how to approach the problem. The first approach we took was the coupling of two tools. So we took a capacity expansion model and we coupled this with a production cost model. So we basically try to use the best of both worlds. In the capacity expansion model, we can use only the reduced time series as described before. And then we check the outcome of this capacity expansion model in a production cost model with hourly data and also with variability and uncertainty attached to see whether security of supply criteria are fulfilled. This is what we call a soft linking of the two models. And this basically enables to use the benefits of the best of both of those worlds. And there is a feedback loop, so we need to do this a couple of times over and over again until the solutions converge. We will get into this a little bit later in terms of some results from this modeling approach. The second approach that has been developed within the OSMOSE project is the so-called graph-based formulation for energy systems. So what you can see here on the left is that we have a temporal breakdown. So we can go still for the different years that we're looking at, and each of those years is broken down into days, and the days are broken down into hours, and each hour could even be broken down into quarter hours. And this is all done here in this hierarchical tree. And on the right-hand side, you can see that the same has been done with the energy carriers. So going here into the example of gas, this could consist of hydrogen or natural gas, and the natural gas could be from synthetic gas or fossil gas and so on. So you can see that this tree here on the right is only a little example. This is the general idea of how the model or the framework that is, has been developed here is being built up. And the idea behind it is that the temporal and spatial resolution can be varied by energy carrier. So, for example, we could have electricity here with an hourly modeling, because this is important for the electricity sector, so that we can make sure that the security of supply criteria are fulfilled. But if we, for example, look at the gas sector, then there is some inherent flexibility in the gas system, which is why it could, for example, be enough to model it only on a daily basis, while, for example, for the heat sector, we could look at a 4-hour basis. Just as an example here, you can obviously pick different time resolutions as you need. So this means that we can make the problem simpler, while at the same time capturing this inherent flexibility in the different system types already within the model. And as an example here of the output of such a model, we have a Sankey diagram with just a little test model here. So you can see here this type of Sankey diagram used here shows you the different energy demands here on the right-hand side, and the different inputs of where they come from on the left-hand side, and these are all interconnected. In total, we have in a concrete model used within this framework more than 120 different technologies included. And there have been a couple of papers already written on this that we can refer you to for further information. Looking at the impact of what has been done here in this model, you can see that the problem size in terms of the matrix that comes here from the different concrete instances of this model, it can be significantly reduced, and this has an impact on the computation time. So you can see here in gray if all the three systems are modeled hourly, and in red if only the power system is modeled hourly, while we have the gas and heating system on a below hourly level. Then you can see that the computation time goes significantly down. while the objective value stays approximately the same, but you can see that it actually goes down a little bit with the less complexity, and this actually shows that there is this inherent flexibility in the systems, which can be interpreted as the lower objective value that we come up here with. The framework is called animod.jl, and it's openly available. You can find it on GitHub, and it can be used, including a lot of data that has been compiled within the OSMOSE project. I would now like to hand over to Jean-Yves Bourmaud from RTE, who will give you a little bit more of insights on the first approach that I talked about, the model coupling approach. So Jean-Yves, over to you.
Thank you very much, Jens. Good afternoon, everyone. So I'm Jean-Yves Bourmaud from RTE, the French TSO. I'm working for the R&D division of RTE, and I would like to present some results on the second approach mentioned by Jens to set up an optimal mix of flexibility. As a reminder, the question was how to catch flexibility value by coupling existing tools. To do that, we need to come back a bit on the definition of flexibility. In OSMOSE, we understand flexibility as the system's ability to cope with variability and uncertainty. Variability and uncertainty occur on different timescales and for different reasons. On the long term, our ability to operate a power system is made uncertain by the difficulty to predict energy policy, evolution of consumer habits, economic growth, things like that. On the medium term, power system operators must face cyclical variations. In demand and in renewable generation, they must also manage plant outage. On the short term, finally, power system operation is constrained by uncertainty through incidents, as well as forecastability of weather-dependent variables like demand or renewable generation. There are obviously many ways of providing flexibility to cope with this source of variability and uncertainty. Broadly speaking, one can either modulate generation, namely generation output, one can modulate demand, one can better interconnect to smooth variations with space, or one can store energy in a different form to smooth variation through time. Several years ahead of real time, we can choose to invest or decommission flexibility solutions, whereas on shorter timescales, we can only activate existing infrastructure. This will be the key question. So next slide, please. Different flexibility solution behaves in different ways depending on the timescale, thus fulfilling different roles in the power system. Here, you see the net load, that is to say, the load minus the fatal generation, like race or run-of-river. In this graph, the net load is decomposed in several relevant timescales, namely annual, on the upper part of the graph, weekly on the medium part of the graph, and daily on the lower part of the graph. Each timescale could be associated with a specific requirement for flexibility. For instance, the annual timescale illustrates how much energy should be shifted among seasons. Here, this example, there is a need for storage in summer and discharge in winter. Unfortunately, as already underlined by Jens, capacity expansion tools, which are very frequently used to study energy mix planning, do not accurately capture the multi-scale nature of flexibility. In OSMOSE, as mentioned by Jens, two options have been considered to tackle this issue. Here, in this part of the presentation, we will focus on a way to address this limitation based on existing operational framework and tools. That the objective is to foster a quick dissemination of the proposed solution by using tools people are already accustomed to. Our proposal was to catch flexibility by soft linking a capacity expansion model with the production cost model. We favored an iterative approach where the capacity expansion module first proposes a mix whose security of supply level is then assessed by the production cost model, which in turn signals under or over investment to the capacity expansion model for the next iteration. The notion of under or over capacity or over investment is based on the null value. Next slide, please. Yes. In energy mixes with a very high share of variable renewable energy sources, it is absolutely essential to take into account sector coupling when assessing flexibility requirements and provision. Indeed, devices that couple different energy carriers, such as electrolyzers or fuel cells, as far as electricity and hydrogen are concerned, modify the load curve. And thus, they modify the flexibility requirements. But at the same time, they can also provide flexibility by modulating their power consumption and therefore their hydrogen output in this case. Therefore, optimal flexibility is a very ambitious title, as already underlined by Jens once again, in particular because the merit order of decarbonization solutions heavily depends on the list of options we considered to meet, for instance, the European pledges of the Paris Agreement. And this list is the combined results of technological maturity trajectories on one hand, and political decisions on the other hand. In this work, a limited number of options has been considered, namely rice, gas units, nuclear, electrical vehicles, heat pump, electrolyzers, fuel cells, and batteries. Obviously, a longer list would yield different results, but the first and main goal of work package 1 was to develop and test a methodology. However, we think that our results lead to general conclusion, and we hope to be able to convince you about that. Next slide, Jens, please. In our scenarios, in 2050, power to gas stands out as a key decarbonizing solution. Once electrolyzers are installed, they turn out to be a key provider for seasonal flexibility. As we can see in this generation demand stack. This stack illustrates the transfer of energy from summer to winter, thanks to electrolyzers producing green gas in summer, when the sun is abundant, and thanks to generation units running mostly on this green gas in winter. One of our findings is that if we allow our planning tools to co-optimize power to gas and various investments, we can further reduce European CO2 emissions by allowing gas generator to run 100% on green gas. Moreover, such a high penetration of power to gas leads to the price being primarily set by demand instead of generation. This debunks the myth that a system with a high share of VRES should drive the price to zero for long periods. Next slide, please. A second interesting finding concerns the interaction between flexibility sources, and it shows how important it is to have a holistic vision of flexibility in order not to be challenged by unanticipated behaviors. At first, we expected some competition and even intertemporal competition between batteries and electrolyzers, due to the fact that electrolyzers can rather easily provide short-term flexibility when in operation, just by modulating their green gas production. In practice, we observed a kind of cooperation between them, as illustrated by the generation demand stack in the left-hand side. Batteries and pump storage plants as well store electricity in excess during sunny hours, as shown by marker 1. Then, they discharge during the night, as shown in marker 2, which allows, in turn, electrolyzers to run outside sunny hours, marker 3. As a general result, the average capacity The average capacity factor of electrolyzers is increased, as well as the total generation of green gas. On the right-hand side, we use a flexibility indicator developed by Work Package 1 to present the flexibility provision by timescale, namely annual, weekly, and daily again, and for different technology. Without going into details, it shows that interconnections play a major role for all timescales, on par with electrolyzers, while batteries only have a role for the daily timescale. In fact, the power grid can leverage all other flexibility solutions. And this value of grid flexibility exists even in simulations without any limit for gas storage or gas transmission. Taking these limitations into account would even increase the flexibility value of the power grid. It should be noted that this collaboration among flexibility providers appears as a result of a system-wide optimization. In practice, in order to reach this optimal behavior, collaboration between flexibility providers and access to interconnections must be fostered through appropriate market design. Next slide, please. In such prototypic studies, as you may know, data collection, cleaning, and model development are time and resource demanding tasks. In our case, they accounted for more than 90% of the work, especially because assessing the security of supply of our scenarios required to accurately reflect correlations between countries and between weather-dependent variables such as load, wind, and PV generation. To address this data challenge, Work Package 1 built upon existing open data, weather data from the Copernicus Climate Change Service, load data from the H2020 project Plan for RES data from the Pan-European Climate Database from ENSURI, and finally, for electric vehicle data, the JRC. Can you press the button, please? For the animation, yes, thank you. In order to promote transparency and constructive criticism and modeling, Work Package 1 is in turn making the full dataset publicly available. You will find in this dataset data for 33 European countries. So first of all, correlated load and VRS time series, then thermosensitive electrical vehicle time series, and finally, pseudo day-ahead forecast time series, which are consistent with the pseudo-realized time series we used and consistent with the evolution of uncertainty when nearing to real time. Now I give the floor to Ricardo Pastor for a focus on integrating innovative flexibility options in the context of planning, operation, and stability. Thank you.
Thank you, Jean-Yves. So my name is Ricardo. Thank you. Good afternoon to everyone. My name is Ricardo Pastor. I'm a project manager and researcher at R&D Nestor, Portugal, and I will move now to present this work. You can move now, okay? So in terms of the work, it consisted in three main activities focused on the integration of flexibility options at three different levels. First, at planning level, a tool for the planning of flexibility options, the DESPlan Sizing and Siting Energy Storage tool, was applied to the Portuguese power system, taking into consideration the OSMOSE scenarios for 2030 and 2050. At the operational level, the available flexibility options were analyzed and using PS Mora for the continental southwest region, including Portugal, Spain, and France. Also for the same scenarios for 2030 and 2050. And in terms of stability analysis, a dynamic study was performed on a portion of the Italian power system, which was updated according to the installed capacities considered in the OSMOSE scenarios for both time horizons as well. We can move forward, please. So first, considering the planning context, which focus on the sizing and siting of energy storage options. The aggregated time series from OSMOSE scenarios for 2030 and 2050 were provided and redistributed using a methodology developed in the project into the more detailed model of the Portuguese transmission network. It was detailed up to the TSO-DSO interface, which in this case goes from the 400 kV level at transmission up to the distribution level, which starts at 60 kV. So the model of the Portuguese transmission network was provided by REN, the model for 2029. REN is the Portuguese TSO, and it was provided under an NDA, and it was upgraded according to the capabilities considered in the OSMOSE scenarios. We can move forward, please. So in terms of results for the scenario current goals 2030, the complete year was simulated, so 8,760 hours, and congested cases were identified and solved using energy storage. In terms of the congestion cases, they were detected in 32% of the time for this time horizon, and the power system presented significant levels of renewables penetrations. The congestions were up to 8% of the rated limits of the lines or transformers, and the energy storage solutions found, they were between 2 megawatt and 20 megawatt hour, up to 28 megawatt and 28 megawatt hour. On the right side, it's possible to see an example of an overload in one branch. You can see the red line as the branch limit, and the figure below is the energy storage response necessary to avoid this overload. We can move to the next. So in terms of the results for scenario current goals for 2050, the same approach was done as in the previous one. But in this case, the congestion cases were detected in 49% of the period of analysis, and the power system showed a much higher renewables penetrations. And you can see there are some periods in which solar production is even higher than the national demand. For example, in this figure, we see from 11 to 1 p.m. Basically, we can see that solar is above the line which represents the national demand, and congestions that were detected, they reach up to 55% of the rated limits of some lines or transformers. The energy storage solutions found were between 15.6 megawatt and 15.2 megawatt hour, up to 172 megawatt and 383 megawatt hour. So as in the previous slide, on the right side, you can see an example of another branch that was overloaded. We can see the red line as well as the branch limit. And in the figure below, you can see multiple energy storage units providing multiple responses on the buses necessary to avoid this overload. It was noticeable that in the case of in this specific case of the 2050 scenario, there were some additional cases of power flow inversion in some transmission substations due to high levels of embedded renewable production at the distribution side. So moving now to the analysis of the available flexibility options studied using PS Mora. In this study, only the continental southwest region was considered, including Portugal, Spain, and France. This analysis was based on the definition of long-term scenarios and later the available flexibility options for each cluster. All of this data was used to first run Valor Agua, which provided the expected value of water per week, and after that, running PS Mora for the operational reserve assessment. Please move forward. So focus now on the most interesting results related to the 11 climatic years for scenario current goals 2050. In this slide, we can see that the loss of load expectation for all the climatic years simulated. Two things can be highlighted from these results. The first is that the reliability indexes will differ as the operating conditions change. And the other one is that LOL, so the loss of load expectation results, increase mostly derivative from the congested interconnections. Going deeper into these results, the simulation results suggest that most of the problems occurred in France, and an important recall here, we should say that the energy flow between France and the rest of Europe, which was mostly exporting, was in this case modeled as a fixed demand for France. Please move forward. Now looking at the results from the sensitivity analysis on the increased flexibility in France. In the base case of the scenario current goals 2050, it was assumed that 5% of the interconnection capacity between France and Europe would be modeled as flexible. The reliability indexes show that the average where all the climatic years were used, then as we increase the flexibility available at the interconnections, the reliability indexes become more alleviated as expected. For instance, for the last configuration, on the right side, so for run 4, in the case of the flexible interconnection between France and Europe is increased in 30%, this would reduce the loss of load expectation from 0.74 hours per year to 0.14 hours per year, which is a 81% reduction, or the expected energy not supplied from 1.9 gigawatt hour per year to 370 megawatt hour per year, also 81% reduction. Moving to the next slide. Similarly, the sensitivity analysis of interconnection capacity reinforcement was performed. The starting point was the same considered in the previous slides, and in this case, for each run, the interconnection capacity within the continental Southwest region was increased, giving a special focus on the interconnection between Spain and France. As can be seen in the last run, so run 4, a 7 gigawatt interconnection reinforcement will decrease loss of load expectation, again from 0.74 hours per year to 0.26 hours per year, so less, reducing in 65%, and the expected energy not supplied from 1.9 gigawatt hour per year to 720 megawatt hour per year, with a reduction of 62%. Move forward, please. So lastly, regarding the dynamic study, which was performed to a portion of the Italian power system, the Sicilian power system, this analysis took into consideration the OSMOSE scenarios and flexibility options available for the corresponding cluster for 2030 and 2050 time horizons. It was focused on the stability assessment, namely frequency stability, large perturbation angle stability, small perturbation angle stability, and voltage stability. Please, next. So I'm sorry for the table, but actually with these colors, it's probably easier to follow the information. So focusing on the OSMOSE scenarios for 2030, on the large perturbation angle stability, all the cases were related to the frequency in which the connection with continental Italy was kept. The frequency does not go outside normal operating conditions. On the island mode, the loss of inertia and primary regulation coming from continental Italy makes the frequency generally less stable. On the generation, please back. Not yet. Generation loss events, frequency moves out of the normal operating conditions, yet the stability can be ensured by the provision of flexibility from flexible loads, demand side response, without any load shedding. Please stay. On the small, previous, Jens, please. On the small perturbation stability, it has been found that the system does not present any major stability issues, with the exception of a high export dispatching profile, which presented a not properly damped oscillatory mode. Nevertheless, this stability could be improved thanks to synthetic inertia contribution from wind farms and the tuning of a relevant PSS. power system stabilizers. In terms of voltage stability, it has been noticed that when Sicily is importing power from continental Europe or it is disconnected, its loadability margin there and hence the voltage stability is reduced. However, the reactive support from renewable energy sources contributes for the increase of the overall loadability margin in all the dispatching profiles. Now, please move to next slide. So looking at the 2050 scenario, and concerning the large perturbation angle stability, what we can see is that it is ensured that in all dispatching profiles and for all the events that were simulated, except one very specific and very unlikely operating condition, the results show a very stable network. Nevertheless, it is possible to reach a stability in such critical operating condition by considering the contribution of battery energy storage systems and demand-side response to the support of these perturbations. In terms of the small perturbation angle stability, the dispatching profiles in which renewables support frequency control is not active. There are some cases with low-damped electromechanical modes, in particular some inter-area modes. And like for 2030, it was proven that it can be stabilized using the contributions from synthetic inertia provided by batteries and battery energy storage and wind farms, and the proper tuning of power system stabilizers at relevant generators. Since 2050 scenario presents a lower percentage of synchronous machines compared with 2030, a higher voltage instability has been observed. However, with the flexibility provision from renewables, it can be supported and able to manage all the operating conditions studied. Thank you, Jens. I think we can move now, and I will pass the floor to you.
Yes, thank you, Ricardo. And before we end, we just want to go into a couple of key takeaways from work package 1. And one of them is that when we look into these future scenarios, the capacity expansion models that exist should be improved to better account for flexibility. And we could do this on the one hand side by coupling existing planning tools with dispatch models, or we can go into this graph-based approach with an integrated investment and dispatch model. So the two ways that we showed here in work package 1 are both viable and promising for the future. Flexibility needs and sources will have to evolve significantly between now and 2050 on all timescales. And work package 1 here developed some contrasted scenarios that have been referred to question flexibility needs in Europe on the 2030 and 2050 timescale. You can find full scenario data on this and on all the calculations that have been done on the OSMOSE website. And two key takeaways from these calculations probably here. One of them is that electrolyzers, if they become common in our future power system, could be a huge game changer. So this is one takeaway from the supply side, but we also had a look on the demand side, and the flexible electrification of such demand can actually provide a major share of the needed system flexibility, and it needs to incentivize by proper regulation. And especially the electricity demand for the hydrogen production, so just as the mentioned electrolyzers from before, is very flexible if the hydrogen pipelines and storage will be deployed to match the production with the final consumption. Overall, we have to say that we obviously need a holistic view, and we need to have an improved coordination by the market design, and the topic of market design, as I said, is addressed in OSMOSE 2 in work package 2, and there will be another webinar on that tomorrow. So please sign up for that if you are interested in further details. For the part that Ricardo just mentioned, we also have a couple of additional key takeaways. So flexibility will be the key for our successful energy transition within Europe. And we can see here with the Desplan simulations of the Portuguese power systems that have been done. And they showed that the grid congestions in the set scenarios may occur as a result of these high levels of race in the system. So we have to go for a smart use of the flexibility options in the system, and energy storage can here provide a valuable technical alternative for flexibility provision. The simulation is done with the PS Mora tool for the interconnected continental southwest region in Portugal. Considering these short-term race generation uncertainties, help to validate that the flexibility options that were proposed by the scenarios are more or less viable. And we can see here that the role of fast response and flexible units, for example, such as hydropower plants that play an important part in large parts of the European power system, provide to be key when dealing with forecast deviations in our renewable energy sources. And finally, looking at the simulations that were done for Sicily for 2030 and 2050, they show that the dynamic system security can be ensured and enhanced thanks to the flexibility provided by the renewables. So, for example, synthetic inertia and energy storage controls in terms of frequency control, and also demand by demand side response. So we have to say these scenarios for 2030, 2050 that have been developed here in the project have been done in the very early stage of the project. So with the later results that came up, they have also been updated a little bit. In terms of the next stage that we're looking at here for the work that has been done in OSMOSE, first of all, you will be able to read a lot about all this work on the OSMOSE website and a couple of upcoming publications. But we also want to keep working on this. So, for example, by improving the soft linking feedback loop that we mentioned between the two models, capacity expansion and dispatch. We want to improve or enrich the sector coupling model in the optimization step, so the capacity expansion model, but also in the simulation step, which is the production cost model, by looking, for example, at more investment candidates, but also include other energy carriers like methane, the gas grid, and heat. And then there should be also feedback on the environmental impact beyond CO2 emissions, looking at system-wide LCA, so in terms of, for example, resource depletion, human health, and others, to account for the environmental impacts beyond just the impact of CO2. And looking at the other approach of any mod with the integrated model, also here we would like to go for a couple of methodological advancements to further increase our spatio-temporal details, because currently we just look at one limited single year of hourly time series, but we want to look at different climatic years to be considered in the planning process. If you want to read more about Work Package 1 and also the remainder of the OSMOSE project, we would like to refer you to our website, where we have a couple of deliverables from Work Package 1 and obviously also the other work packages, which are linked here. There is a last part of the project that has been not presented in this webinar, which looks at the synergies between flexibility services. So this is the last mentioned deliverable here, also available online. And then there are a couple of publications also referenced in the website, where two of them are currently in the publication process or short before submission, so stay tuned for some more results from that. So thank you very much. If you have any more questions beyond what can be answered now in the Q&A, then here you can see our contact details, and feel free to email us. And as I said, have a look at our website, osmose2020.eu. And now we would go for the Q&A. So please feel free to post any questions that you have in the chat. And I can already see that there is one question here by Arthur. So how did you build future electric demand profiles, especially for 2050, and what are the elements taken into account? So this has been done within the scenario generation, so there are a couple of elements that are important in here. Obviously, we look at a very large amount of electrification in terms of the models used. They basically look at the final demand for energy, not specifically electricity, and the capacity expansion model then can decide on how this energy demand is fulfilled. And obviously, it looks at a large scale of electrification here in general. So then the electric demand profiles depend a lot on the technologies used and the degree of electrification that is happening. And in terms of the scenarios that were built, the external setting that we chose was mostly based on the amount of CO2 emissions that would still be allowed in the system. And this then led to the decision of the model, depending on all the different technologies, cost data, and availabilities, let's say the options of how much it would be available. And this is how the demand profiles then were built in terms of electricity. I don't know, Jean-Yves, would you like to add anything in terms of the profiles?
Yes, thank you, Jens. Maybe a small addition regarding the practical process for generating and providing those time series. Basically, we based our profiles on the data published by the Plant4S H2020 project, which did a tremendous work in preparing a large set of data. We benefit from the fact that they based their computation on published data regarding the weather condition published by the Copernicus website. And these data are reanalysis between 1982 and 2020. Therefore, we had a reference regarding the weather data. The way the Plant4S data are organized are threefold. They make the distinction between a non-thermosensitive profile, a thermosensitive profile, and a profile for electric vehicle. The thermosensitive profiles are then derived with one profile for each Monte Carlo year, each climatic year. When looking into detail into it, we were quite satisfied with the non-thermosensitive profile, but we had some issues with the thermosensitive profile. Therefore, we decided to adapt them. And a specific issue, as mentioned by Jens, is that in 2050, we expect a huge electrification. And in practice, this huge electrification will first take place in the area regarding heat. And we expect a large development of heat pump over Europe, which is a huge switch from now, where only roughly France and Czechia are thermosensitive. And we expect that in 2050, all European countries will be thermosensitive. Therefore, this point is essential to master. We had also an issue with the way they modeled electric vehicles. And therefore, we used data from the GRC to completely rebuild EV time series and adding a thermosensitive part to it, because it was not the case in the Plant4S data. And for the last clarification and the fact the way the load time series evolved from now until 2050, in the process, it should have in mind that we multiply the profile, the early profile over 1 year, which is a factor, in fact, and sends to add up to 1 by an annual volume of energy. And the simple fact that the outcomes of the capacity expansion modules make a distinction between 2030 and 2050 between, for instance, the annual energy for heating results into different and quite distinct and contrasted time series for the overall load. I don't know if my answer is clear and fully answer your questions. Please do not hesitate to comment if it's not the case. Thank you.
Okay, there are two other questions about DSM. So is DSM considered within OSMOSE, and how will load payback be scheduled after load disconnection? So there is some flexibility from the demand side given. So again, we have to distinguish between the two model approaches, so to say, that we took in the long term, and in the graph-based approach. As I mentioned, there is some inherent flexibility, for example, from the heating system, which is depicted by the lower level of timescale detail in this part. So let's say 4-hourly level instead of an hourly level. So this is one of the options of how heating demand can sort of say be shifted, because it just is shown as more flexible in this model type. But there are also basically direct demand side measures available. And for the other part, maybe Jean-Yves, you can say something about that.
Yes, we have to introduce a specific part of flexibility regarding the electrical vehicle profile, and namely a rate of 6% of the daily energy which can be shifted from between the different hours of the day, with a restriction so that the shift is lower during the day than during the night, in order to reflect the fact. So it's an expectation, that's it was ours, that the fact that people would more easily connect at night when at home than during the day when at work. And for the heating profile, the modeling was a bit more rough, and the shift was limited to 4 hours, if I remember well.
Okay. There's another question related to this. What are the flexibility capabilities associated with each generating technology? So I assume this might refer a bit in the direction of whether the model also looks at any unit commitment, for example, ramping up and down. So in this case, we have to mention that the model here looks at the whole of Europe, and Europe is broken down into 96 or 99 zones. So we don't look at single generators or generating units. So we are not able to capture the flexibilities thereof, but there is a way of how some must-run conditions basically are depicted in some generation technologies, at least for AnyMod. There are details in the description of AnyMod of how this is done. But basically, we don't look only at merit order principle, but we use kind of must-run conditions so that we better reflect this must-run part, or the flexibility that we have from there. So it's not purely merit order based, because then there would be, so to say, too much flexibility from these generating technologies in it. And Jean-Yves, I don't know if you want to say something about the anti-res part.
Yes, regarding anti-res, so the production cost model, we can fully model the way the generators can behave, taking into account technical constraints such as the minimum stable power, the minimum duration, the the startup costs, things like that. In the context of OSMOSE, we did not take into account all those so-called dynamical constraints because the setup with 99 clusters was quite large. But yes, basically the merit order is respected in our results. And if we had more time, we certainly could improve on that by adding new dynamical constraints and check the sensitivity of the results with respect to that. An additional comment is that the simulation time step in Antares is 1 hour, and we are fully aware that when looking at flexibility, the intra-Pauli phenomena might become important. But we have decided not to address that, but rather to address the problem of the issue regarding the uncertainty, the ex-ante uncertainty, and the way when you get nearer to real time, the uncertainty is reduced, but at the same time, the flexibility levels that you may use are also less numerous. And it's in our studies, it's in the deliverable. We had a Europe-wide study about reserve, which illustrates what I'm referring to.
Okay, thank you. Do we have any more questions from the audience? At least I don't see any additional questions on the chat. So we still have a few minutes left. So yeah, let me just mention again that we have all the outcomes of the model available, or of the project available on the OSMOSE website. So all the deliverables are already linked there. If you want to get more detail on any of the parts presented today, or also on the topic of the synergies, then please go to our website. And we will also post any upcoming publications. So there are at least 2 or 3 additional papers coming up that we will also post them on the website, and probably you will also see it on Twitter or LinkedIn. And the paths that have been started will be ongoing. So we'll keep on developing the different models and scenario calculations that we've done here. So stay tuned for more details and more outcomes. Since I don't see any more questions, let me just thank again our 2 speakers, Jean-Yves and Ricardo. And if you come up with any other questions that you couldn't think of now, then please feel free to contact us. You can see our email addresses here. Otherwise, you can also go to the website and find the different deliverables there. Everything is linked, and we're happy to hear from you if you have any more questions. Okay, so thank you very much for attending.